Spiking neural networks are modeled after the sparse and event-driven characteristics of biological neural processing and hold promise for enabling ultra-low power artificial intelligence. Today, I'll be talking with Ilkin, who is studying the hardware-software co-design of sparse neural networks as part of his PhD research. Welcome to the podcast, Ilkin.
Thank you, Luke. Thanks for having me.
Great. So at a high level, what is a spiking neural network, and what are some of the challenges related to the hardware-software co-design of spiking neural networks if we want to one day deploy this technology to solve problems?
Yeah, so let's. This is a two-part question. The first part, like, what is spiking neural networks? So spiking neural networks are the same artificial neural networks, SNNs, but more biologically plausible, meaning the activation functions in SNNs are slightly different than those in ANNs, like ReLU or 10H activation functions. So we have this binary activation functions in SNNs that resembles brain, because brain also communicates, as far as we know now, binary in a binary manner. The communication is represented as binary. So that's the first part of the question. And then second part of the question, what are the main challenges? So we will detail on this further, but the first challenge is obviously the training. The learning algorithms for SNNs are still not good. The mainstream training algorithms are basically is the backpropagation. That's what produce state-of-the-art results. But that is the main obstacle. I would say that disable SNNs to be deployed on real-world applications, specifically like static datasets, like vision datasets. Let's say static. Like real-world vision datasets, or language NLP datasets. So that's the first obstacle. The second obstacle, apart from training, is the true hardware architecture to leverage this sparsity in the activation, in SNN activations. Remember, we said the SNNs are more plausible. Biologically plausible, meaning they have binary activations as opposed to integer or floating point values in ANNs. But they currently, the research community in SNNs lack efficient hardware, let's say, efficient spiking deep learning hardware to take advantage of such hidden gem, I would say. Yeah, that's the second obstacle to deploy them in the real world applications.
Cool. Yeah, so to summarize, the first issue is with the backpropagation, where backpropagation doesn't necessarily fit into the paradigm of spiking neural networks. And then the second obstacle is the lack of efficient hardware to take advantage of these hidden gems.
Yeah. So we could, backpropagation still is used for SNNs. So for example, my papers, we trained our models with the backpropagation, and you can go and then any state-of-the-art research paper in SNN, they're all mostly trained on backpropagation, unless they are explicitly proposing a specific learning algorithm. But the way the problem when you train spiking neural networks with backpropagation is the fact that the neuron model is non-linear, meaning it's linear. It's one bit. It's not like derivative. Like you can take derivative of let's say spiking neurons. So what people use today is what's called surrogate gradient functions that approximate output of these spiking neurons. I understand this is a very detailed thing. Probably you haven't seen this before, but you can think of there's an extra abstraction layer in order to enable SNNs to be able to be trained via backpropagation.
I see. Interesting. Cool. So to go into some of the introduction questions, why exactly are spiking neural networks so energy efficient?
So, I mean, this is actually a dilemma, I would say. They are so-called efficient, but again, so let me answer this: why they are energy efficient, and then I will answer why they are not energy efficient. Well, obviously, the sparse processing, meaning when you have, let's say, 50% of your neurons at a given time are inactive, so you don't have to process, you don't have to read weights, you don't have to do multiplication for the half of these neurons. So this is where so basically half of your max multiply accumulation goes away when you have let's say 50% sparsity, 50% density. Again, this is contingent upon whether your hardware is as efficient as taking advantage of that, but that's where the efficiency comes from. So this is what my early part of my research dealt with, proposing hardware architecture to leverage this sparsity in activations. But now, when it comes to the second part, why they are not energy efficient, it is a fact that there is this time step notion in spiking neural networks, which doesn't exist in SNNs, meaning spiking neuron accumulates input currents over times. So this number of time steps, like how long is it gonna keep accumulating the input currents, like input weight data, is it depends on how long how many time steps is needed in order to achieve a certain accuracy. So let me give you an example. Let's say that I have a specific task, a data set, that I want to achieve. Let's say the state-of-the-art accuracy for this data set in SNNs is 95%. Now, when you bring this task and train a spiking model, spiking network, if you set time step to 5, let's say, you might not achieve that same accuracy, or you can get way lower. So the point is that as you increase this time step to this certain point, your performance of your model, I couldn't say like linearly or exponentially, but performance of your model increases as well. So that is why. So there are certain tasks that are very complex that you need to set higher time steps, and that means that while SNN process this certain task just once, but SNN is going to process it, let's say, 15 times because the time step size is set to 15. So basically, you cancel out the benefit from the sparsity, activation sparsity, when you have such repetitive phenomena in your processing. So this is where, unfortunately, again, it depends on algorithm, training algorithm. Backpropagation is not efficient for SNNs, meaning it leads to higher time steps, longer time steps. Yeah.
Interesting. So the idea here, the first idea that you were expressing is about how if you have sparsity and you have a hardware that's able to activate it, if you only have maybe 50% of your neurons active, now instead of needing to make calculations on 100% of your neurons, you only have to do it on 50% of your neurons. So you save a lot of processing power if you can actually leverage that. But then the second part that you're talking about is this idea that spiking neural networks accumulate over time. So there's this it feeds back into itself type of nature.
Yeah, exactly. It's like RNNs, recurrent neural networks. Definitely, yeah. It's a good analogy.
Okay. And so with a spiking neural network, and you can specifically specify like 15 times for it to repeat. Is that how it works, or does it figure it out by itself how many times to repeat?
Yeah, that's the thing. It's kind of like empirical. So you should basically try and error in order to determine what number of time steps you need for this specific task.
Okay. So over time, through testing, you'd be able to determine generally how many time steps to give for that specific task.
Right.
Okay.
Yeah. I mean, you could do it. It's empirical. Fundamentally, by definition, it's empirical. But you could automate that problem where, like certain hyperparameter search tools like Optuna, you can basically optimize the number of time steps using that Optuna-like hyperparameter search tools. But it's empirical.
Okay. And then when doing this process where it iterates through, does it need to leverage all of the neurons? So if we have 50% sparsity, are we doing that 50% 15 times if we have the time step?
Okay, sparsity. Now let's actually then define sparsity because we skipped that part. So we're talking about dynamic sparsity, which is more analogous to human brains. Dynamic sparsity means a subset of neurons are active at a given time. It's not static, meaning it's not across all time steps. So in the context of SNNs, the number of at each time step, let's say we have 15 time steps, at each time step, sparsity is different. So, but you can say that it's always at this, like if it's 50% at time step one, typically this is what the characteristic we have been seeing. It varies like 55, 45 in a specific range, but it doesn't, like, it's not a specific number across all time steps.
Okay, I see.
Yeah.
I see. So yeah, when we're talking about dynamic sparsity, that means that at each time step, a different subset of the neurons are going to be active and likely be in some range, but it'll be different for every time step.
Yeah. Every time a specific fraction of neurons are active.
Okay. Yep, that makes sense to me.
By the way, I can give you, so like you can think of convolutional neural networks as a perfect example of sparse processing, because it's a structured processing. So think of fully connected layer, right? Fully connected layer mean each neuron in a post-synaptic layer is connected to all of the neurons in the presynaptic layer, right? If we can visualize it. But what is happening in convolutional neural network? Each neuron in postsynaptic layer is connected to only a subset of, like, the filter size. If you have 3x3 filter, you only have connection in the presynaptic layer to 9 neurons. So this is sparse processing, meaning you only need to activate certain neurons, but it's structured sparsity, meaning you exactly know the locations, addresses of the connected neurons.
Okay, I see. Yep, that makes sense. Cool. And so the next question is, what exactly is sparse coding and sparse connectivity, and how can hardware designs exploit it to conserve energy?
So sparse coding refers to, at least in the context of digital hardware, it refers to how do you represent your activation values. Like, there are certain coding mechanisms today, like bitmap or run length coding. I think I have heard of that too. But bitmap I've seen it's the most commonly used representation or coding in general neural networks, both ANNs and SNNs. So what is the connectivity? So we can answer this question. So sparse connectivity, let's actually touch upon a little bit neurobiological foundations of this connectivity. So human or other animals have different regions of their brain. And for example, there is this primary visual cortex, right, which is responsible for processing the visual inputs from the eyes. And then there is this cerebrum, but the specific part of the neurons that are responsible for cognitive functions and reasoning. And then there is this limbic part, which is responsible for emotional and short-term learning part of the brain. Now, at each part of these regions, sparsity is different. For example, the primary visual cortex has lower sparsity. It has higher density because you can intuitively think vision is very complex, high intensity, and you need a lot of neurons to be activated to process specifically the vision. Whereas, for example, the limbic part, which consists of hippocampus and amygdala, you only need lower number of neurons, meaning you have higher sparsity. Your hardware should be able to decode the active fraction of the neurons dynamically, and then do the multiplication and accumulation MAC operations for only those neurons. Because when you think about in a non-sparse hardware, the main issue is that you have these resources, your MAC units, but they're not active in a given time because the input is 0, neurons are not active.
Okay, that makes sense. And so what are some key considerations in the co-design of hardware and software for SNNs?
So on the hardware side of the things, so this is again sparsity dependent consideration. In general, when you design your ANN hardware, one of the big decisions is to determine what is the size of your systolic array, what is the shape of your systolic array. And this problem of determining your hardware structure becomes more cumbersome when you go to sparse hardware, because you have this third dimension here, which is sparsity, meaning now you don't just need to decide let's say if I have a task, a data set that's this big size, or set of data sets, multiple data sets. I need this much, this big hardware. Now you need to also know the sparse characteristics, at least beforehand, of these data sets, the tasks, in order to decide your final hardware structure. So I would say the hardware size is the first consideration. The second consideration on the software side, let's go back to these surrogate gradient. If you remember, I mentioned in the beginning that are employed, that are basically bridge, playing a bridge role to enable SNNs to be trained by backpropagation algorithm. This surrogate gradient, there are certain functions, the smoothing, approximating functions that are smoothing the output of the spiking neurons. But then which function would you go with and select? And we have seen during our empirical experiments that certain functions not only have impact on the accuracy, it has also impact on the sparsity of the model. So that is another, on the software side, that's one consideration, selection of your training hyperparameters, specifically surrogate gradient function selection. Second is like the neuron model, such as leaky integrate fire or LAPQ neuron. They also have certain non-negligible role in terms of accuracy and sparsity. And then the third consideration, I would say, third and then fourth consideration on the software side. Actually, third could be combined with the second one. The neuron, not only the neuron type, but the neuron parameters, such as the threshold value of the neuron that it needs to suppress in order to fire, or the decay factor of the neuron. It also has impact on model's accuracy and sparsity.
So to summarize, the first one is the size of the model that you're using, because that's going to impact your systolic array and the shape of your systolic array. Then the second one is the hyperparameters, such as how you're calculating the surrogate gradient for the backpropagation and other considerations like the smoothing function. Thirdly, the neuron type. So if you're looking at the integrate fire or a different type of neuron, and the threshold of value for the neuron to fire or the decay value. Fourthly is the quantizing model, so how you quantize it. And then fifthly is your input encoding, so how you convert the data into the spiking domain.
That's correct.
Okay. Yeah, very interesting.
Yeah.
Cool. And so what is static sparsity and what are its advantages?
So static sparsity, so let me first say this, static sparsity is not biological phenomena, it's completely digital phenomena, because again, sparsity in brain is completely dynamic. In the context of digital hardware, static sparsity refers to the weight sparsity. Remember, we have been talking about activations, and the reason it's static, because once you train your model, and then when you deploy it for inference, the connection, it's static throughout the entire inference lifetime. So static sparsity, obviously in the context of existing, for instance, the real-world commercial application of static weight sparsity can be seen in NVIDIA's GPUs, starting from Ampere and then Hopper, where you can train your model and then you can prune your model. So static sparsity is not it's not inherent. It's achieved by pruning the model, meaning you train your model, you don't immediately get the static sparsity from the model. You need a pruning step. I'll talk about what's the advantages, but this is, I think, key information to be aware of. So you have to prune your model, meaning you have to set a threshold and then set all the weight data across your model to 0 if it's below that threshold, and then retain the value of the weight if it's higher than that threshold. So that after pruning, you do recovery training. But the main advantages of static sparsity is the memory. So essentially, you are halving. I'm talking about, again, the commercial application of static sparsity in GPUs. There is 4-2 structure. So we're talking about static structure sparsity, meaning half of your weights are 0. So what this means is, if you have multi-billion parameter model, half of them, you need half the size of the memory of the original model.
And so what are some typical activation functions that you use with the SNNs?
So commonly, we have used, like most commonly used in SNN activation function is latent area fire. But then the second we have seen that has been used in the past in the research papers was LAPQ neuron. Empirically, in our experiments, we have seen that LAPQ neuron really perform well for certain, specifically event-based data sets, like input data that comes from vision data, dynamic vision sensors, DVS sensors. LAPQ neurons are absolutely crafted for these data sets. So that's what I could say about neuron types in the SNNs.
So the next question is, how do SNNs differ from ANNs in terms of spatio-temporal dynamics?
Again, ANNs don't have temporal dimension. They don't have like time steps. They have just one time step. So they don't have temporal sparsity. In terms of spatial sparsity, obviously SNNs have much higher sparsity. In terms of temporal dynamics, ANNs don't have any sparsity, no firing, no sparsity whatsoever. In terms of spatial firing activity, SNNs has much higher compared to ANNs, fundamentally because of the neuron type.
What are some types of input encoding methods that can be used to translate real-world data into spikes?
So rate coding is prominent coding mechanism in SNNs, but there is also temporal coding options as well. So the main advantage is this is also task specific. Certain tasks perform better in the certain data sets, perform better in the rate coding versus some of them performing better in temporal coding. But the fundamental advantage of, let's say, temporal coding is they have extremely high sparsity because at a given time, you can think of only one neuron. Each neuron can fire only once across the time steps. We're talking about temporal coding, right? So if we go back to the beginning where we were talking about why SNNs are energy inefficient. Why? Because this number of long time steps, repetitive, that we have to recurrently process, right? Now, if a neuron is going to only fire once throughout these time steps, then it's good. Then that means that you will have very high, very low density in your processing, and even a hardware that is not efficiently leveraging sparsity still will benefit from such extreme low density in firing activity. But the problem with temporal sparsity is there has been research papers that are proposing certain temporal coding mechanisms, but they're not open source, they're not reproducible. So like there is no, so let's say open source code that you can go ahead and then train a certain model and then make sure their fair generalizability of the model. So that is the main disadvantage. And the open source models currently that are available, they perform the temporal coding, input coding there performs quite poorly. So that's why rate coding is mostly available, and most papers that are proposing these certain ideas they use basically rate coding mainly. And then lastly, there is direct coding, meaning you don't have to code your input. You can just pass your input to the model, but then you have to change your input layer of the model. Let's say you have multi-layer SNN, and you have this first layer that is not an SNN spiking. It's not a set of spiking layers. It's kind of like ANN layer that can receive raw data set inputs. But it's not purely like ANN because the activation functions are still leaf neurons. So this direct coding approach is an emerging approach, but it has at least the last two papers, ours papers, and then another paper published at the Yale University by researchers there. The direct coding has much higher sparsity, much higher accuracy, model performance.
Okay, interesting. So this new idea of direct coding, which is where you have the first layer, which is not an SNN, which is just an ANN, and then having that feed into the SNN layers has shown a lot of promise recently, it sounds like.
Yes, that's correct.
Very interesting. So what types of tasks would SNNs be particularly well suited for?
Recently, it's been shown that input data from DVS cameras are much well suited for the SNNs, like gesture data set, like DVS gesture dataset from, for example, DBS cameras, they have much inherent characteristics for SNNs because you don't have to convert input into spiking domain. The inputs are already in the spiking domain. So you don't lose any accuracy. And then the second advantage of these datasets is the fact that you have this recurrent or repetitive approach in ANNs as well, right? If you were to pass this dataset into an ANN model, you would still have to process it like multiple time steps. So let's say you have just the datasets, right? You have this and then this and then this. So the way that this image, it's not like the output from a DBS camera, it codes the changes of which neurons are changed. So if a neuron that didn't change, there is no value in that location. So it's zero basically. If a neuron changes, what is the difference in that change? Let's say you have this gesture, now you have this gesture, right? Now neurons in here are mostly the same, right? But neurons were here like this before. Now this finger changed like this. This means that the neurons here, the values of them have changed. So that means that almost 80% of the image neuron values are the same. Only this region of the neurons are different. So the model has to only process the difference values, the subtracted values in this region. So what I'm trying to say is that the efficiency, the execution characteristics in terms of multiple time steps is the same across ANN versus SNNs for this DBS datasets.
I see.
So both these datasets are well suited for SNNs because they don't lose accuracy by these conversion mechanisms, and second, they have the same execution characteristics as the ANNs.
I see. Very interesting. Cool. Also, what did your experiments show on how model hyperparameters influence SNN sparsity and hardware efficiency?
Yes. Yeah, we touched upon this shortly before, but I will quickly summarize briefly. So one major influence was brought by the surrogate gradient functions. So specifically selection of the surrogate gradient impacted model performance and model accuracy and sparsity. The second was I would say, neuron selection, specifically which LAPQ versus leaf neurons, and then which threshold and beta value of a selected neuron also has impact on model accuracy and sparsity. This third parameter that impacted the hyperparameter impacted was the bit regime or precision. What is the data format of your model, weight and bias, basically, that impacted the activation sparsity, because activation is still binary. We are not quantizing anything in activations, but we quantize the model from floating point to integer, 4-bit integer. Then the activation sparsity goes up. So that was the third important hyperparameter that was impacting huge, I would say significant, across data sets, like 12 to 15% increase in sparsity, activation sparsity.
I see. That makes sense. And what did your experiments show about how the beta leakage factor and the theta, which is the firing threshold, impact the performance of the models?
So this was, unfortunately, this is the thing. This is not consistent. There is no direct relationship between beta value and the firing intensity. Meaning, let's say you can't say, as I increase beta value so beta value changes between 0 and 1, right? Because it's a decay factor. Like 0.8 means you are decaying 20% of your membrane potential every time. So what I'm trying to say is it's certainly not linearly, or there's no relationship between the firing intensity of the activation versus the beta value. The same thing goes for the threshold as well. Unfortunately, it's empirical. So you need to search. It's like a hyperparameter search. I think, for example, finding certain initial loss value, for example, so we are already doing hyperparameter search for SNNs for finding best hyperparameter value. What I'm trying to say is the same thing can be applied, should be applied to beta and threshold in order to find, fine-tune the best value for these for a specific data set.
Interesting. Okay, so in a similar way to the hyperparameters, we need to test in order to find the best beta and theta for that specific case.
Correct.
Cool. So what's next for sparsity-aware hardware design?
So the next thing, I would say like the programming model. So programming models for these sparse accelerators, specifically for dynamic sparsity, I think it's a very promising directions that, like, for a given model, how would you compile hardware? So essentially a framework to map your hardware, map the model. A similar compiler frameworks we use today to map the model across a systolic array. I think it's a huge, there's a huge opportunity in research opportunity in finding different mapping strategies, mapping given model into sparse hardware. Other than that, different sparse representations could be explored. Like maybe bitmap is not the best option. Maybe run length coding or different completely novel bit sparse data format is better suited. So I think to summarize, compilation, mapping, and data format, activation data format representation are promising directions for hardware design of sparse hardware SNNs.
Great. And what university degree do you have, or are you currently pursuing?
Actually, I've graduated. I have graduated from University of Arizona with electrical and computer engineering PhD program. By the way, we have open sourced our papers, the source code, the hardware implementation, and the training framework are almost completely reproducible. I mean, unless you don't wanna deal with Vivado. Vivado is one of the most Xilinx Vivado I'm talking about, because in order to run your hardware experiments, you will need to be Xilinx Vivado. It's one of the most obnoxious tools, unfortunately, in the world. But most of the training scripts, hyperparameter search, are mainly reproducible, including the surrogate gradient exploration, neuronal exploration, quantization, are reproducible and open sourced.
I see. And is there anything else that you'd like to shout out? Any websites or any other resources that you'd like to shout out?
I mean, certainly, SNN Torch by Jason is has been the most useful framework for me. SNN Torch is basically a wrapper for PyTorch. I used it, and many students, and many professors have used it, even probably in commercial use cases, used to train SNNs. And the way essentially they use autograd function. Are you familiar with autograd in PyTorch?
I'm not familiar with that.
Yeah, autograd is a functionality in order to it's a feature to add new functionality into PyTorch. So that's how SNN Torch is implemented, because it replaces the neuron, the activation neurons, with the SNN neurons. And these surrogate functions, they also implemented using autograd functionality. So yeah, I want to just give shout out to the SNN Torch. It's very useful.
Very interesting. Yeah, we'll put a link to that in the description. Did you present this paper at a conference?
Actually, my advisor is traveling next week to Malaysia. He already is probably, because the conference is next Monday. It's called MC Associate Symposium. It's one of the major symposium in associate design. Yes, we are presenting next week.
Very exciting.
Yeah.
Do you have any advice for people who are looking to move into the field of SNNs?
I mean, if I would have to, let me put it this way, if I would have to restart this, I would start, and if I would have to meet to work on SNNs to advance the state of the art in SNNs, I would rather go with the learning and training approaches, put my efforts in that directions, and then think about sparsity, because training and learning is a much more urgent problem for SNNs than this sparsity exploitation.
Great. And the last question is, do you see SNNs being viable for commercial use cases in the near term?
I mean, there's actually current startups working on, and they have commercial products. And I can name, for example, it's called SNNs. It's in Netherlands in Europe. They use vision DVS cameras, and they have chips to efficiently process. Like they have integrated DVS cameras with the SNN neuromorphic chips, and I think it definitely depends on the use case application. For the current LLM, like massive training sort of application use cases, it doesn't seem viable. SNNs have very low chance in that direction. But if continue learning, where you will update your weights data on the fly as you go, such use cases, it's a very it's not. I mean, there is no such application currently that might have such characteristics where at least there's no real world application viable currently that could be seen. But that is where SNNs might shine, maybe.
Perfect. All right, that's all my questions. Thanks again for coming on the podcast, Ilkin. It was really great talking to you.
Thank you, Luke. Thank you very much for having me.